Hello everyone, welcome to the purple classes of the Rus Indica IAS Academy, and I welcome each and every one of you. Desh Badala, Padhai Badlu. So today we will be starting with the GS paper 1. GS paper 1 topic, GS paper 1 topic, and that is geography topic. Geography is the, like, we call it as half of the portion of that paper is made up of geography, GS paper 1. So under that, we will be talking about the first topic, that is called salient features of the word physical geography. So first of all, we will be talking about the various physical geography. Under the physical geography, we will be also talking about uh, the geomorphology, geomorphology. Then we have climatology. Then we have oceanography, right? Oceanography will be there. Then we will have biogeography. Okay, then we have environmental geography. So all these topic we will be talking one by one. So it is going to be a big topic, and we will be discussing all the things in detail over here. So let's start with our first topic. So before going ahead, every time I tell you, like, first of all, I always discuss the syllabus. Okay, so this is the syllabus that is there. So we will be doing this part. This is the geography part. This is whole geography part of the UPSC mains examination GS paper 1. So these all topics belongs to the geography part, from salient features till important geophysical phenomena. Okay. So today topics, total 12 topics that we are going to discuss today. Exactly 10, 12 topics. Origin of Earth, theory related to Earth formation, age of the Earth, method of finding the age of Earth, motions of the Earth, Earth magnetosphere, interior of the Earth, distribution of oceans and continent, theories related to the uh, continent and ocean movement, major tectonic plates, mechanism of movement of tectonic plates, plates boundary. So these all topics that we are going to study today. See, first of all, you might be thinking that these are the very very basic topic. Yes, these are the basic topic, and people don't know these. In the UPSC examination, your fundamentals has to be very very strong. Your fundamentals has to be very very strong. Then only you can build upon your answer. Then only you can, because if you don't know the fundamental, you will not able to build your answer, and then there will disaster will happen. Okay, so you should know each and everything, because whenever any question comes, you don't know from which topic it can come, but you will have all the content material. You will have all the content ready, content related material. If you revise this 4 5 times, if you revise this 4 5 times, automatically you will be able to frame the answers. Automatically the points will be coming into your minds, and you will be able to write a very good answer. So let's start with our session. So origin and evolution of Earth. Earth is a member of solar system that everybody know, and it is believed that origin of Earth is connected with that of a solar system. How solar system has been formed, and this is all connected with the solar system. So, but how the solar system came into being? How solar system came into being? How? So for that, lot of theories are there. Lot of theories are there. Some have limitations. Some are providing some kind of answer, but there is one theory which is more or less is accepted by everybody, that is called your Big Bang theory. Big Bang theory, and you might have heard about this word, and you might have read also about this word. So it is said that the universe is started from a single point that is very very dense. It is infinitesimally small point. Okay, there is a point which is highly pointed, and it is a very very dense point. It is a very very dense point, and this is called as singularity. It is called, this point is known as singularity, right? around 13.8 billion years ago, 13.8 billion years ago, this point started expanding rapidly and in a form of a big bang, a blast. It throws the matter into the space. Okay, it is of very hot material. The material was very, very hot and it is just spreading throughout. Like here, you can see this is a singularity point. It started expanding and it broke into this whole part. Okay, start getting away from it, right? It is said that around 3,80,000 years after the Big Bang, the universe started cooling down. The universe started cooling down, and because of the cooling, the energy of the atoms slows down, and because of that, they came these uh, atoms, proton, those who are traveling freely, started coming together, and they started making matter. Okay, they started making matter. Okay, so this matter clumps together due to gravitational attraction. As more matter get attracted and more gravitational pull started creating, led to the formation of stars, galaxy and cluster, right? And right now also it is still expanding and the galaxies are moving away from each other. That means this is a point, it got expanded and the things are moving like this in an open area. That means everything is going further and further and further. This is the Big Bang theory that we have discussed. Right, now we are moving towards the nebular hypothesis theory. It is yet another theory. It has been given by Immanuel Kant. Okay, he has proposed this through the Pearson Simpson Laplace significance who has developed. What this theory tells about is that this whole solar system has been made from a rotating cloud of interstellar gases. I think there are a lot of interstellar gases are there. So these gases are called as nebula. Nebula. Slowly, this nebula started contracting. Slowly, that nebula started contracting. You can see here, dust grains are there. Slowly, it has started contracting. Slowly, it started contracting. And as the contraction began, there was a heat up that happens, and the matter nearby that area become denser. So matter, whatever the matter was there earlier, the matter was far apart, so this is less dense. When the matter comes nearby, it become denser. Okay, so it lead to the formation of proto-sun. Okay, so this matter lead to the formation of this proto-sun. When the matter comes they come together, it created a proto-sun. And around this proto-sun, there is a disk that has been created because of the accretion. So you can see here, this proto-sun is getting created, and outside here, black points you can see, right? So this is another material is there, which again gets into the disk-like pattern they have formed, and this get converted into the planet. So people say that what is the evidence that this has already happened? So you can see that disk-shaped region of gases and dust. If you see the stars, if you see the planet, there is a disc shaped region of gases are there. That means if they are, if that is thing is there, that means it has to be present during that time also, right? So the motion and composition of celestial body in the solar system aligned with the prediction of nebular hypothesis. So nebular hypothesis, whatever nebular hypothesis said that the motion of the celestial body, whether planet, whether sun, whether moon, whether we have stars, they all align with the prediction what has been given by the nebula. But the exact mechanism how this nebula started, that means in the starting this cloud was there, but from where this cloud came is still not fully understood. Okay, and even some outer planets we are not able to explain under this theory. Okay, so but there are a lot of challenges are there, but it is also widely accepted theory of the solar system formation. Okay, Then we have tidal hypothesis. Tidal hypothesis is given by Jeans and Jeffrey. Jeans and Jeffrey created a biparental origin of sun, like how sun got created. Okay, so it is said that there was a star and there was a primitive sun. Primitive sun means we cannot call that as sun, but it looks like sun. Okay, so there was a intruding star. There was a big star which was there, and there was a primitive sun. Primitive means in the starting stage. What was that sun? Not now. Earlier the sun was of different category. Right now the sun is of different category. But during the starting phase, when the sun was getting generated, there was a star that is going from nearby this sun. So because of that, a bulge is created because of this gravitational force of the intruding star. Okay, because of the gravitational force of this intruding star, huge amount of material from this primitive suns get extracted. This matter was ejected from the sun, and this matter got condensed into various other planets. Okay, did you got it? I'll explain one more time. This was a this was a intruding star. This was a primitive sun. So when this intruding star was passing nearby sun, because of the gravity of this intruding star, lot of material from this primitive suns got ejected. Like here, you can see this material. And once the intruding star passed by, this ejected material got condensed into various planets. Got condensed into various planets. Okay. Then we have a protoplanet hypothesis is there. How the planets have been formed. Okay. So again, they said that there is a rapidly rotating material. Material is called as nebula. Material is called as nebula. It has created very high speed rotating mass of gases. Okay, high speed rotating mass of gases, that is called vortexes. Okay, at various places, like here one vortex is there, at this place one vortex is there. So everywhere there are high rotating mass of gases are revolving around certain thing. Okay, so each of these vortex surrounded by a material of the gravitational pull has led to the formation of protoplanets. So everywhere where the vortexes are there, rapidly rotating material is there, they get condensed into protoplanets. And along this big vortexes, there are smaller vortexes also. Like if this is one vortex and there is one smaller vortex is there. So you can call this as Earth, and then you can call this as Moon. Right? So smaller vortex and big vortex. So this big vortex converted into planets, and the smaller vortex got converted into satellite. They got converted into satellite. Okay, so they became satellite of a planet. So like that, that is called protoplanet hypothesis. Is all about. Now, age of Earth. So how we actually find out the age of Earth? First of all, we should know what is the age of Earth by various experiments. By various experiment and various other ways of advanced science and technological measures, it is find out that the earth is around 4.54 billion years old. That means 4.54 billion years old. So 13.8 billion year is the big bang theory, and earth is 4.54 billion years old. So earth has to take long time. 9 billion year after the big bang the earth has formed. Okay, so there are a lot of scientific measure through which we have identified, like radiometric dating, rocks and mineral dating, meteorite study. You know, a lot of meteorites keep on falling on the earth atmosphere every day. Okay, Then Earth's cooling rate, what is Earth cooling rate, and all these things are being utilized in order to find out like what is the age of Earth. So approximately it comes out to be 4.54 to 4.6 billion years. You can say around 30 40 million year here and there, okay, because we are talking in a very very large scale. So 20 40 million years is nothing in the scale, okay. So still ongoing research are going on. You know, we have also sent the Chandrayaan mission, right? Chandrayaan 3. We have sent, we have touched down on the South Pole. Again, it is going to dig the planet and it is going to analyze the soil over there. One more thing is that to find out the age of Earth, by finding out the age of the moon, we are able to find out, because it is expected that the moon is made from the material from the Earth. So by studying the moon, we can find it out like what was the situation during that time, and by that time we will be able to exactly find out what is the age of Earth. So, method used. What are the method used? First is radiometric dating, or we call it as radio carbon dating, because here we are using carbon. So, radiometric dating means we utilize lot of other material also. We utilize is lot of other material also, but under that we utilize carbon also, right? So, we analyze the isotopes of various minerals. We analyze the rocks, we analyze the minerals, we find out the rock sample, we take out the rock sample, okay, with the help of uranium, with the help of potassium argon, rubidium, strontium, and carbon. We do the radio mapping, we do the radio mapping to find out like what is the age of certain thing. So you can see over here, this is that they are taking out that sample from there. Then analysis of meteorite. Meteorite keeps on falling on Earth, keeps on falling every day. Millions of meteorites fall on Earth, but they simply get burnt away because of the friction of the Earth. And some of the big meteorite sometimes do the touchdown on the Earth's surface, and by analyzing these meteorite, we are exactly find out like during the time of the formation of Earth what was the situation, because meteorite is being known that meteorite were there when the Earth and when the universe is getting formed, okay. So, by understanding the isotopic composition of the meteorite, we can infer the age of the solar system, and then we do the extension to our own work. Okay. Now, the next way how you can measure the age of Earth is by the cooling rate of Earth. Cooling rate of Earth means whenever when the earth was forming, when the earth was forming in the formation of the stages, like around like what we call it as it is 4.6 billion years ago, when the earth is forming, it was very very hot, the temperature was in millions. So how the temperature of the earth cooled down, we calculate that, we calculate that. So the rate of cooling of different material, like if some material was in liquid state, it gets solidified its state, okay. So rate of cooling and how the different material got solidified and how much time they take to solidify, we are able to estimate the time that took earth to reach its current state, okay. Then lunar sample, lunar means moon sample. Okay, Apollo mission has been sent, then India's Chandrayaan mission has been sent, because if you wanted to find about the earth, you have to find about the moon, because they are the close related bodies. That is why lunar rocks are being analyzed, lunar rocks are being analyzed by the scientists to find out the age of both the bodies, because it has been thinks that the moon is made from the material of the earth, because when earth was in the formation stage, one meteorite got collided, and because of that collision of the meteorite, large amount of material got ejected from the earth's surface, and then it got cooled over, and then it get converted into a moon. So that is why analysis of the lunar sample will give insight into the age of the earth, right. Now we are moving to the next topic, motions of the earth. Motions of the earth means earth has two important motion, two motions: rotation, rotation and revolution. Rotation earth do on its axis. You can see this axis. Rotation happens on its axis, and revolution of the earth happens around the sun, around the sun. Okay, rotation happens on its axis and revolution happens around the sun. That is a fixed path. Okay, this is called a fixed path, and this path is called as orbit. Okay, you know, like from orbit, like we send satellite to the earth's orbit. Earth's orbit. That means if this is the earth, we send one satellite so that it revolves around the earth. Okay, that is the orbit of the satellite. Similarly, the orbit of the earth or orbit around the sun of the earth, that is called orbit. Okay, now there are certain effects because of the rotation and because of the revolution of the earth. So first of all, we will see what was the effect of the rotation of the earth around its axis. वो अपने एक्सिस में उसको क्या इफेक्ट्स होते हैं. So because of the rotation around its axis, we get day and night. Circle of illumination, you can see here, uh, the sun is being over here and sun is illuminating this part and earth is rotating like this. Okay, as the things goes from here, the sun illumination will go like this and this will part will get illuminated. So since this part is revolving, so every time some other part of the world gets illuminated, right? Because of this, because of the tilting of the axis and because of the rotation of the earth around its axis, we get day and night. Some places days are bigger, some days nights are bigger. Some places they are of 6 months and 6 months. Some places we have a very less days, less sunlight. We have some places we have a very less days. Okay. Then because of the rotation, the Earth at the pole, flatness at the pole, and bulge at the equator. If you see, you will find little bit flatness in the pole, and this can you see bulge near the equator. That is because of the rotation of the earth on its axis. Then occurrence of sunrise and sunset also happen because of the rotation of the earth. Because since the earth is rotating because of the Coriolis force is a very important force which is because of the movement. Because of the movement of the earth, it leads to the generation of the winds, it leads to the generation of ocean currents and oceans. And because of the rotation of the earth, we find that the sun is moving, we find the stars are moving, the moons are moving because of the rotation of the earth. So these are the effects of rotation. Now, what happened if the earth did not rotate? Right now, earth is rotating. All of a sudden, the earth gets stopped. All of a sudden. First of all, you know the Newton laws. Newton laws. If something is moving, it will be moving continuously. If something is rest, it will be continued at rest until and unless external forces applied. You know, have you ever been to in a bus? Obviously, you have been into the bus and suddenly brake happen. Suddenly brake happens, you move forward like this. You move forward like this. Correct. Similarly, earth is rotating. Along with that, our feet are on the earth's surface, so we are also rotating. Since we earth and we both are rotating at the same speed, that is why we cannot feel the rotation of the earth. But if all of a sudden earth stops, we will be thrown out of in the space. We will be thrown out of in the space. So if the earth stops rotating, there will be catastrophic changes to the life. Drastic change in the temperature, automatically the rotation, because of the earth rotation, the heat get distributed evenly throughout throughout the planet. If the sun, sorry, if the earth stops rotating, One part of the earth continuously will be facing sun, and one part of the earth will be continuously facing the darkness. So the part which is continuously facing the sun, because of the stop of the rotation, will be very intense heat, and where there is a darkness, there will be maximum cold will be there, negative temperature will be there. So there will be high temperature variation, and our planet will become uninhabitable. Disruption in atmosphere will take place, because if the rotation got stopped, the heat and moisture will not get circulated. So without rotation, this pattern will be ceased. Weather system will be uh, coming into a chaotic work. Okay, there will be very high tornadoes, very high hurricanes, because of the sudden stoppage of the earth. Massive tsunamis, sudden stop of the earth will lead to ocean to blast away the shore areas. There will be very high tsunamis. There will be devastation. They will destroy the whole coastal areas. If all of a sudden something stops, everything goes move forward, right? Loss of gravity and stabilization effect. So stabilization effect, because of that, because the earth is creating a stabilization effect because of the centrifugal force. Okay, because the centrifugal force counteracts the force of gravity and help in stabilizing the planet. If rotation is not there, our earth will become oblate. So there will be change. The land distribution will get changed, water distribution will get changed automatically. It will lead to the earthquakes, volcanic eruption, because of the sudden destabilization of the land. Okay, sudden destabilization of land, because of the sudden stoppage, magnetic field of the earth will get lost. You know, magnetic field is very important, because they are generated because of the movement of molten iron in the so the earth rotation helps in generating magnetic field because of the molten iron that is there in the core. If the earth stop rotating, this process will stop, and because of that, magnetic field will become weak. And once the magnetic field will become weak, harmful solar radiation and cosmic radiation will bombard the earth surface, bombard the earth surface, and it will stripe away the life from the planet earth. Right now, revolution. Right now we were discussing about the rotation. Now revolution, that we are going to discuss now. Revolution is revolving around sun. That is called once a year. So once the earth rotate from one place to the other, we call it as a one solar year. That is 365 days and 1/4 day. Okay, so that is why every 4 years we celebrate a leap year. So not celebrate, we make a leap year. So this year is a leap year because 2024. Anything which is divisible by 4 is a leap year. Okay, so it is the earth orbit around the sun, that is elliptical in nature. That means if this is sun, the earth is revolving like this is called elliptical path. This is called elliptical path, and there are two position. One is farther point from the sun, farther, that is called aphelion. Farther point of the sun, that means it is the farther point, and the perihelion, it is the closest point from the sun. During the perihelion, the earth is very close to sun, and during the aphelion, the earth will be very far away from the sun. Okay, so what are the effects of revolution of the earth? There are three important effects. Because of the revolution, change of season takes place: winter, summer, autumn, spring, right? Length of day and night, you see that in winters the day is of shorter length, and the night are you get the darker very early. Shifting in the wind belts, some winds start blowing during the summer month, some winds start blowing in the winter month. They keep on changing their position like that. Then polar variation of the, there are some other things that we need to discuss regarding a polar variation. So there are three north poles of the earth. One is called geographic north pole, one is called as uh, magnetic north pole, and third one is geomagnetic north pole. So there are three north pole, they are not the same thing. Geographical north pole is the topmost part. Magnetic north pole where the magnetic field lines are interacting. Where geomagnetic north pole is where geomagnetic lines are interacting. Okay. So geographic north pole is a northern tip where the axis around the globe spins. North magnetic pole, it is slightly towards the south. Exact location is not always the same. It keeps on deviating from one. So Earth magnetic field is always changing. This shows that. Then North geomagnetic pole, it is the northern axis of magnetosphere. Northern, that is the far away, away from the Earth, magnetosphere, which is helping and protecting us from the solar winds. This is the farther magnetic field. This is a farther magnetic field. North magnetic pole and geographic north pole are being part near the earth's surface, and this north geomagnetic pole are the farther part which help in shielding us from the solar winds. So if you see over here, now we will be talking the topic on earth magnetosphere. You can see this is earth magnetic sphere is spread like this. Can you see here? And here you can see earth magnetosphere. This magnetic sphere is being created by the earth's core. Okay, so earth magnetosphere is a region surround our planet where dominant magnetic fields are, is that on the earth itself. Okay, magnetosphere where the magnetic field is that of earth itself. So from the interior of the earth at this point, from this point, it is spreading in the outer space. It is spreading in the outer space, and it is also forming a protective shield in the outer space. So whenever any streams of charged particles from the sun comes, this magnetic field lines interact with them and cancel out them. So that is why it helps in protecting the life on the earth. Without the earth magnetosphere, there is no life. We cannot imagine any life on the earth. So there are certain lines, sir, there are certain technical words that are related to earth magnetosphere. One is magnetopause. Magnetopause where the boundary where earth's magnetic field meets the solar wind magnetic field. Okay, where the earth's magnetic field and the solar magnetic field winds interact, that is called magnetopause. Then magnetotail. This is a elongated region of magnetosphere that extends away from the sun, opposite in the direction of solar wind. That means where the solar wind were going, it is opposite to that direction. It is like a tail. It is like a tail behind the earth. You can call this as a, this is, you can see magnetotail. Can you see this magnetotail are there, right? This magnetotail, right? Behind the earth, and these are the line which are stretching of the magnetic field lines by the solar winds. Then Van Allen radiation belts are there. Van Allen radiation belt is a region within the magnetosphere where charged particles, primarily electron, proton, are trapped by the Earth magnetic field. Okay, so this is being find out. This is being find out by the James Van Allen. Okay, and this is a highly charged region. This is a highly charged region which is also help in protecting the radiation from the sun. Then we have our own ionosphere. Okay, you know, troposphere, stratosphere, mesosphere, ionosphere, right? We have a layers of earth surface above the earth surface. So there is a layer that is called ionosphere, which is ionized by the solar and cosmic radiation. and it plays a very very important role in interaction between Earth's magnetic field and solar wind. And because of this presence of ionosphere, the harmful radiation of the sun do not reach to the Earth's surface. Then you see there is a word called the aurora, or we call it as aura. When charged particles from the solar wind interact with Earth's magnetosphere, there are solar wind particles, there are Earth magnetosphere particles. When they interact, or when they collide with each other, they produce a very colorful display that is called auroras. Okay, so you can go for there is a two places which is called auroras borealis, that is northern lights and in the northern hemisphere, and aurora australis, that is southern lights in the southern hemisphere. So at particular places only you can see this. And I think in Norway, Sweden, you can go and find this northern lights and southern lights. In the southern lights you have to go to the southern hemisphere below equator, and for the northern lights you have to go above equator, right? So when these charged particle interact, it create a colorful uh, light display that happens because of these interaction of the charged particles, right? Now let's discuss the internal structure of the Earth. We all know that there are a lot of layers from our Earth crust to the center, of Earth, right? But before going through that, we have to find out how we are able to find out like what is there inside the Earth. That means there is something that we have done, or some scientific experiment has been already been doing in order to find out what is there inside the Earth, what is the structure of the Earth, whether it is hollow, whether it is solid, whether it is semi liquid, or whatever, what type of it is. So there are two resources: direct resources, or direct inferences, and indirect inferences. Direct inferences happen when you dug a deep drilling project. Okay, there is a deep drilling project where you start drilling, and I think up to 12 kilometers you try to drill, and based on the type of material you got it from that drilling, you are able to find out what exactly is there at each level of the Earth. Then you find out from the volcanic eruption, because volcanoes magma is built in the mantle. We'll discuss all this mental. So from the volcanic eruption, the ashes, the magma, whatever comes out, doing research doing research on that data, we are able to find out what type of earth interior it is. And then after that, some indirect sources are there: analysis of the matter, what is there inside, meteors that reaches earth. Look, lot of meteorite that reaches earth. So we think that the meteors and earth, they are all made from the same material. So if we start studying the meteor and their composition, we are able to find out from where the how the earth has been made and what is there inside the earth. Then gravitation also is the one indirect way through which we can understand exactly what type of surface, what type of interior of the earth it is. Then magnetic field line, then seismic activities, like your waves are there, right? Earthquake waves are there. By studying that earthquake waves and everything, we are able to find out what is there inside the earth. So these are the direct and indirect. So they can ask you question on like what are the direct and indirect sources, where how you will be able to find out the internal structure of the earth, right? So earth interior is being broadly divided into three parts, that is crust, mantle, and the core. Okay, crust is the uppermost part, mantle is the middle part, and core is the last center part. Okay, under that also there is further divisions are there. There are further divisions are there. So if you can see over here in this pic, this part is called crust. This part is called crust, and we call it as lithosphere. We call it as lithosphere. Lithos is the crust in which we are sitting. We are making everything. Okay, the earth's surface. Okay, in the lithosphere only you have the oceans also. So in the oceans, the earth crust is little bit downward, and on the upper part where all the things, all the land area is there, normally this all part is solid. This is all solid. Then after that, the mantle start. After that, the mantle, just below the lithosphere, there is mantle. There is upper mantle and below mantle is there, right? And asthenosphere is just below the lithosphere, which is the mantle, right? So we will be discussing each and every part. So this is mental. From here we start with the core, upper core and inner core. So they have already written like what kilometers, after what kilometers the things are having. So you can see here from 0 to 100 kilometer, you are having a crust, earth crust is there. Okay. Now from after 100 kilometers up to 2900 kilometers, you have an area of mantle. You have an area of mantle. Then from 2900 kilometers to 6378 kilometers, you have outer core and inner core. It is not up to scale, but it just give you an idea regarding that. Now crust. So the uppermost part of the earth is known as crust. So crust is having a thickness of 5 to 10 kilometer in oceans, and the in continent it is 35 kilometers. Maybe if you are standing on a continent or if you are standing on a land, the thickness of the crust will be 35 kilometer. And if you are in ocean, then the crust size from the below the beneath the ocean floor, the crust is up to 5 to 10 kilometer below that. Okay. So close to 55 to 70 kilometer in orogenious belt, the thickness is 55 to 70 kilometers. Then once the crust is over, there is a Mohorovic civic discontinuity. Mohorovic discontinuity is there. So you can see here we have a crust, here we have mantle, and just where this border area lies, it is Mohorovic discontinuity. That means between the lower crust and upper mantle. Okay, this is the lower part of the crust, and this is the upper part of the mantle. So between this, we have this discontinuity, right? So lower boundary, it is a continental region just underneath the zone of superficial sediment. Okay. Now, how the crust is made up of? So upper part of the crust is made of Sial. We call it as Sial. Silicon, silica and aluminium. These are the two major components through which this crust is made up of. Okay, up to 11 kilometer Sial, right? And the lower continental crust, below that, it is made of SIMA, SIMA, silica and magnesium. It has a thickness of around 22 kilometers. So Sial and SIMA, that is silica and aluminum upper crust, and below that SIMA, that is silica and magnesium. So this is the breakup of like the crust is made up of what elements, what sediments, and all those things. Now we are coming into the mantle. Mantle is the most important. We call it as sometimes as the powerhouse of the earth. Powerhouse of the earth, because here only is the internal energy source of the earth is there. It is the source region of most of the internal energy. Because of this mantle only, the sea floor spreads, the continental drift happens, orogeny happens, and everything. Earthquake comes because of that. All these things are there. So it is just below the Mohorovic discontinuity and up to a depth of 2900 kilometer, and this mantle has a thickness of 2965 kilometer. Okay. Then once this mantle, we have crust, and here we have core. So between crust and mantle we have Mohorovic discontinuity, and between mantle and core we have Gutenberg-Wishart discontinuity. Gutenberg-Wishart discontinuity. So this discontinuity is there between metal and core, right? So density of metal, since P and S wave, which are related to earthquake waves, record an increase in their velocity in the mantle. So whenever the P and S waves are there in mantle, so their velocity is increases. So that means the material of the mantle is denser than the crust. That means crust is less denser and mantle is denser, thick, right? You got it? Now there is further division is there, lithosphere. We have already done, like lithosphere is the upper part, the crust. Lithosphere is the crust and asthenosphere is below lithosphere, and it is in plastic state. Plastic means it is not, it is semi-liquid, semi-liquid in state. Okay, lithosphere we call it as crust, that is the upper part of the Gutenberg layer. That is all till there, till all there we have lithosphere. And below that, below lithosphere, where the lithosphere is ending, we have asthenosphere, which is plastic semi-liquid, and from where we can call that as mantle has started. Okay, so now core area. Core area is the totally central part of the earth. It is the innermost part of the earth which is separated from mantle by Gutenberg Wishart discontinuity. Okay, mantle and core, and between this we have Gutenberg Wishart discontinuity, right? So under the core area we have inner core, and then we have a outer core. Outer core. Outer core is in liquid state. Outer core is in liquid state and inner core is in solid state. The main reason is that at inner core we are around 5,000 to 6,000 kilometer below the earth's surface. The pressure is so high that anything there becomes solid. Anything over there becomes solid, okay, because of the increased pressure. So inner core inner core is solid in nature and outer core is liquid in nature. Okay, so in outer core S wave do not pass because S wave can only travel in solid areas. So this shows that outer core is made up of liquid. This is one reason. This is the one reason that we call it as outer core is made up of liquid, because S waves that are generated by earthquake waves do not pass from the outer core, which shows that outer core is liquid in state. So it is like an inference that we can get, since S waves are not passing, so outer core has to be liquid. Okay, so the pressure of the core is around 3 million atmosphere and temperature is around 6,000 degrees Celsius. And inner core, which is solid in nature, so that means the core area, it says that it's been made from nickel and iron. Nickel and iron. Nif. We call it as Nife. We call it as Nife. Nickel and iron. Nickel for Ni and iron for Fe. Nife. Okay, the core is made up of nickel and iron, which is solid in nature. Now, this is what the summary regarding that. Crust is 5 to 70 kilometer continental, primary granite and basalt, solid in state, thinnest layer. Mantle is 70 from 70 kilometer to 2,900 kilometer, made of silicates minerals, solid and viscous fluid, right? Divided into upper and lower mantle, right? Here only all the tectonic plate movement all happens over here. Then from 2,900 kilometer to 5,150 kilometer, like outer core, and 5,150 to 6,771 inner core. Okay, so iron and nickel, Nife, iron and nickel, Nife. So this is liquid in state and this is solid in state, and this helps in generating magnetic field. So core is helpful in generating magnetic field, and mantle is helpful in driving the plate tectonics. So this is the main role of the mantle, and the main role of core is to generate magnetic field, and for the main role of the mantle is to help in like plate movements. Now we move into the next topic, that is called distribution of ocean and continent, right? We know that the oceans and the continent which we see today, they were not same million years ago. The earth is changing, plates are moving, so whatever continent you are seeing today are present. But we don't know what happens 1 million year ago, what happened 20 million years ago, what was there 1 billion year ago, what was there, right? So many theories have been put forward to tell, right, how the oceans have moved, how the continents have moved. So we are going to study some of these theories over here. Under that category, we have the most important theory is the continental drift theory. Very important theory is continental drift theory, which has been proposed by Alfred Wegener in early 20th century. According to him, if this is the earth, then there is a huge land mass. This is a land mass, and around that whole water was there. So that is a single land mass. That is called Pangea. Okay, Pan. That is called Pangea, and the oceans are called Panthalassa. Oceans are called Panthalassa. Now, why this continental drift theory has gained importance? It is because of the evidence it gave. Because if you go and find out, like if you go to Africa and if you go to South America, they were both joined earlier. The way it shows like a jigsaw puzzle. Okay, in the find of a jigsaw puzzle, fossil evidence that has been found in Africa, similar fossil evidence they have found in South Africa, which shows that these two continents were earlier joined together. So, what forces has led to the break of this? So, if you can see here, the era Permian period 225 million years ago, we have dinosaur period was there, right? So Pangea was connected like this. Around 200 million years ago, Triassic period was there where Laurasia and Gondwana land started breaking up. Then Jurassic period, then 150 million. Slowly, you can find out this. Say this is Africa, this is South America, okay, this is North America, this is we have our Greenland part, okay, and this is India that is going on, this is Australia that is going on. Then Cretaceous period 65 million year ago, you can see this South America got divided, then North America, here we have Asia, we have Africa, we have India moving towards that, Australia, Antarctica. Then after present days, right now you can see this is the main situation. Okay. So this is a mechanism because of the convectional current that were there. Ocean crust started to breaking up, right? So modern understanding says that there are plate tectonics which moves because of the tectonic forces within the earth surface. So with this concept, earlier people were not eager to express this and they don't want to accept that, but slowly it had gained acceptance because of the discovery of the plate tectonics. When the plate tectonics was not discovered, nobody was accepting this idea. Once the plate tectonics theory has developed, the people started accepting this idea. Now, convectional current theory. Convectional current. Okay. I told you we have mental. Mental is semi liquid, right? So, this theory, convectional current theory of uh, formation of continents and ocean, is being given by Arthur Holmes. Arthur Holmes. So it says that Earth interior drives correct convection current. Okay, here you can see this convection currents are there. Okay, they rise up, they fall down, they rise up, they fall down. Okay, this is the magma. This is the hot and molten magma which rises and fall down, and here it creates a ridge break. It creates a break over there. So heat from the earth's core create convectional current, and it helps in tectonic plate movement. Okay, you can see these are the tectonic plates. Okay, these are the tectonic plate, gray color are these tectonic plate. Because of this convectional current, this tectonic plate moves on the opposite side. So evidence supporting this is because of the sea floor spreading theory. You can see if you go there where the ridges are there, you will find this convectional current theory. Magnetic striping, because magnetic striping on both the sides, and as we go on the opposite side, the magnetic striping keeps on getting older. That means you will find the latest magma, the new magma near the ridge, and as you go away from the ridge, you will find the older magma. Okay, then regarding the earthquake patterns and volcanic activity, you will be able to find out that. Okay, so this theory again revolutionized the whole process of understanding the tectonic plate movement. Then sea floor spreading theory was given by Harry Hammond Hess. How the sea floor spreads, how the sea gets created. If you can see over here, there was a land. Because of the convectional current, there was a breakup, rupture happens. Because of that rupture, the land got break. The area where the land gets break was filled with water, and as more and more area it breaks, more and more water gets filled over there. Okay, so this mechanism is because of the formation of the convectional current, and because of that sea floor started spreading. Okay, 1960s this theory came into being, and the main concept is mid oceanic ridge. You can see like if you go to Atlantic Ocean, most famous ridge is there. It passes from the central of the Atlantic Ocean. You can see it's like a where the land is getting formed, ocean ridge are getting formed. Okay, it is a place where all the like all the material from the blasting of the uh, material from the convectional current get deposited, and as you move away from these places, the material gets older and older, because you at the place at the ridge only you will get the new material. Okay, if we go by findings, so pattern of magnetic polarity recorded in the ocean floor provide evidence that is free floor that means magnetic polarity, if you find over here, is also giving the reason that yes, sea floor spreading is happening. Okay, so these are some of the supporting events are there. So this is the theory is all about, sea floor spreading theory. Then plate tectonic theory, a very important theory, and which is the base for all the other theories. So this plate tectonic theories is said that the earth crust is divided into plates. It is not a single landmass. The earth crust is divided into plates, and these plates keeps on moving over the mantle. Okay, so this theory has been given by Mackenzie, Parker, and Morgan. So Earth lithosphere is divided into large and rigid plates, and these plate floats on the semi-fluid asthenosphere, that is mantle, right? And these plates keep on interacting with each other. These plates keep on interacting. Either they are coming together, or either they are leaving together, or either they are getting transformed together like that. Okay, so these plates tectonic explain all other theories. Okay, so the data that we have got from the paleomagnetic data and ocean basin data, type of earthquakes and volcanic activities, because if we go by earthquake and volcanic activities, plate tectonic theory has a huge role in finding out the earthquake and volcanic activity. Because of this plate tectonic theory, we are able to exactly locate from where the earthquake can come. Okay, and there are a lot of features are there, like mid oceanic ridge are there. Okay, then we have trenches are there, mountain ranges are there, which supports this evidence that something is some kind of plate movement is happening. You know, we have Himalayas. I wanted to give you an example. Himalayas. You know, when the India part was moving towards the Asia, okay, this was Asia, Eurasia, sorry, Eurasia, and this is India. Between Eurasia and India, there was a big ocean. As India collided with Eurasia, the sediments that are there on the sea floor get raised and give rise to Himalayas. In the sediments of Himalayas, you will find the fossils of fishes, which shows that between India and Asia, there was a huge ocean that was there. So this is again one of the evidence which shows that the plate movement has taken place and the plate got collided, and because of that Himalayas generated. Okay, so this is plate tectonic theory, and here I wanted to explain you one thing. There are three type of plate boundaries that we are going to read in the next slides. Now, since we have discussed about the plate, so there are major plates and there are minor plates. So there are seven major plates are there. That is Antarctica and the surrounding oceanic plate. So this is the Antarctica plate. This is the Antarctica plate, big plate. Then North American plate. North American. This is a North American plate if you see. This is a North American plate. That is a single plate. Then we have a South American plate. Here you can see this is a South American plate. Again a big plate. Okay. Then we have a Pacific, very big ocean, right? Pacific plate is there. This side we have a Pacific plate is there, big, very big ocean plate. India, Australia, and New Zealand are coming under single plate. Where is India? We have Indian plate here, on Australian plate. This is a big plate into which Indian Ocean is also there. Okay. Then Africa and Eastern Atlantic plate. Africa, this is Africa and Eastern Atlantic. This part, Eastern Atlantic plate is also part of the uh, African plate, and Eurasian plate and Oceanic. Eurasian on the top one. Eurasia plate is there. Okay, these are the seven major plates are there. These are the seven major plates are there. Okay, so if you see Pacific plate, North American plate, Eurasian plate, African plate, South American plate, Antarctica, and Indo. So you can remember that. You can remember this data where these plates are there, what is their outer boundary. So I have given you in the tabular column just to make you understand the thing so that you can just have the look at that. Then we have a minor plate. Some minor plates are also there. Chota chota plate. Cocos plate. Cocos. If we go back into that, so if you can see here, we have this is as a Cocos plate. Nazca plate. Nazca is this a oceanic plate is there. Then we have Arabian plate. We have this Arabian plate is there. Philippine plate. Here we have a Philippine plate. Carolina plate. Can we see Carolina plate? Caribbean, Carolina. Okay, it is not here. Let me see. Caribbean, Carolina. Okay, it is going to be on the eastern part. Okay, fine. I'll just let you know in the other class also. Okay, then we have a Fuji plate is there, which is on here Pacific part. Okay, so these all minor plates, major plates, these are all moving, they are all interacting, and wherever they are interacting, they are causing volcanic eruptions or earthquakes. Okay, we know Pacific ring of fire, where the Pacific Ocean has a whole ring around them, right? So here all the plates are meeting, maximum plates are meeting over there. So because of that, even people say that why Japan is getting a lot of earthquake and tsunami. Japan is situated over three plates. Japan is situated over three plates, and these three plate getting one is getting transform boundary, one is divergent plate, one is convergent plate. Because of that, Japan is every day getting sometimes smaller tsunamis, smaller earthquake, or sometimes major earthquakes like that. Now, what is the mechanism of plate movement? Why this plate movement work? First of all, there is a mantle convection. Okay, we have a molten magma. Molten mantle is there, which causes the plate to move. Okay, heat energy is there that move. Then ridge push. So we have mid oceanic ridge are there. which keeps on deviating. Old crust gives away to the new crust. Slab pull, there are subduction zone. Subduction zone means where the one plate is moving inside the other plate. So the sinking plate is called as subduction plate. Okay, so we have this plate is coming and one more plate is here. So this plate is going down. So we call this as subduction. We call it as subduction plate. And wherever this subduction happen, here we get earthquakes. We get earthquakes. Similarly, you can see Himalayan plate. In Himalaya, we get in Nepal we get lot of earthquakes. Why? Because in the Nepal only this subduction zone is there. Okay, that is why Himalayas and the upper part of the India gets lot of earthquakes. Then mental drag, when the semi-fluid ionosphere dragged along the convectional floor, so because of the plate also moves like that. Transform faults, faults are there where the plates are broken, faults are there. So if anything is moving along these plates, it generates forces. And plume activity, hot springs, hot spots, mental plumes, that red magma, okay, they all create a kind of uplift drag. They all create a kind of uplift and volcanic activity because of that plate started moving. Okay, now there are three type of plate boundaries. So we have discussed seven major plates, right? How they are interacting. The two plates can have a divergent boundary. The two plates can have a convergent boundary, or the two plates can have a transform boundary. So what is the meaning of divergent boundary? So if we say that Indian plate is there and we say Eurasian plate is there. Okay, if Indian plate is going like this and if Eurasian plate is going like this, then we call it as a divergent boundary, like that. Okay, so where tectonic plates move away from each other. So when the two plates move away, between them, between these plates, there is a formation of new crust because new magma will rise over there and it will fill that gap. So if you go to the mid-oceanic ridges like Atlantic Ocean, between the in between the Atlantic Ocean, you can see the new area gets filled up with the uh, magma. Okay, so most divergent boundaries are found along the ocean floor. Ocean floor, you will find that in the mid-ocean ridge, you will be finding out. Okay, so Eastern Pacific rise and mid-Atlantic ridge, you will find this. Rift Valley also occurs. So whenever there is a two plates moving away, so there is a gap that is created. Okay, if we say this plate is there, 1 minute, let me make a diagram. If we say one plate is like this and one plate is attached to it, but all of a sudden this plate move like this plate move like that, so what will happen? All of a sudden there is a valley, so this plate is going like that, so this valley is created, rift valley is created. Okay, so this is the East African rift. If you go, that East African rift is there, which is getting break, and inside that valley, the water is getting filled. We are saying that by around 100, 200 years afterward, okay, or after 1000 years, the Africa will break, and there we will be having one ocean that will divide the Africa in the North Africa and the South Africa. Like South Africa means southern part of the Africa. Okay, then we have a convergent boundary when one plate and the other plate comes together. So in this scenario, what will happen? One plate will go down and other plate will go up. That means the heavier plate will move down and the lighter plate will remain above. Okay, so it lead to collisions. Sometimes oceanic plate converges. So when two plates collided, so there is a force that is created which is called subduction that is created. Okay, so because of that, more deeper oceans get created. There will be a ring of fire that will be created because during the where the plates are getting uh, uh, what collided, so they will generate a volcanic eruption at that place. So there will be huge seismic activity, volcanic activity, earthquake activity, volcanic eruption will happen over there because of the oceanic convergence. So wherever ocean converges, you can see the Pacific ring of fire. Pacific Ring of Fire along the Pacific Ocean. Asia, Japan, South America, and North America. This whole area is covered by the Pacific Ocean. You can see they're all the Pacific Ring of Fire. Then we have a ocean continental curvature. So there is a ocean plate which collide with the continental plate. So ocean plate is denser, so it goes down beneath that. Okay, so it created volcanic arch, trenches, and mountain ranges. The Andes Mountain and Cascada Range in North America are example of that. Then we have continental convergence. So this is our own example. Our own example in India, Himalayas. Okay, so Indian plate, that is continental plate, Eurasian plate, that is continental plate, both collided, and Indian, and when two continental plates collide, neither the typical subject due to their similar density. So nobody gets subducted. Collision lead to the upliftment of the large mountain. So when the collision happens, so there is whatever the material was there, it get uplifted into mountain. You can see Himalaya are because of the continental convergence of that plate. Okay, so Indian plate and Eurasian plate converges together, and because of that Himalayas got formed over there. Okay, so this is convergent boundary. And the last one is transform. Here one plate and this is other plate, so this is going like this and this is going like this. They are not converging and they are not spreading, they are just transforming, they are just touching each other and going away. Okay, so when tectonic plate slides past each other, they neither create this lithosphere, they do not create the land, and neither they destroy the land, but they simply just redistribute. Okay, normally they create fault lines, because of the fault happens. Okay, huge gaps happen, fault happens in the opposite direction, and Sense Andrea fault in California is the best example. A lot of movies are also being made on that. Okay, a lot of science fiction movies are also made on that. So San Andrea fault is a type of a transform boundary fault. Okay, where two plates just pass by them, and because of that a fault is created. Okay, a kind of a fault is created here, a gap is created. So this is regarding the plate boundaries. So today we have done all the topics, and tomorrow we will be continuing this topic in our second session. Okay. So thank you so much. Bye bye. Take care and have a good day.